extreme values of a function. Let me find my camera. Here it is. There it is. Okay. And I guess I should maximize the window. That would be helpful. I wish this little thing would go away. Nope. All right, so section 4.1. Extreme values. Now, extreme values are local maxes and local mins, which are maximum points and max and min values of your graph. And that becomes a big deal when it comes to applications later on in this chapter. My goodness, there's just too much stuff up here by me. Okay. All right, so a little bit of a preview. And I'm going to try to duplicate a simple graph here. Suppose we go up, and then we come back down, and then we go back up, and we come back down. So something like this. Okay, something like that. And so these kind of peaks and valleys are considered your local maxes and your local mins. So if this is an x value of 2, 3, 4, 5, and this is an x value of 5, 6, 7, 8, and an x value of 8, then you're seeing that at an x value of 2, you have kind of a local height or a local max. At the x value of 5, you have kind of a local min. And an x value of 8, you have a local max. So we have local max of, this height would be a height of 2, a local max of 2 at x equaling 2. So your maxes and your mins are your vertical values, your y values. So you have a local max of 2 at x equaling 2. You have a local min of -1 when x is 5. So you have a local minimum of -1. You have another maximum, you have another local max of, let's see, 1, 2, 3, 4, 5, 6 at x equaling 8. So those are your local maxes and your local mins. Well, those are just kind of, the graph has various peaks and valleys in it, and those are your local values. Now we also have this thing called absolute max and absolute min, which means that's as high as the graph will ever get, or that is as low as the graph will ever get. So usually one of your local maxes or one of your local mins can also be the absolute value. Well, if you look at your end behavior on this sketch, you can see that if the end behavior is down, down on the ends, and this is by far the maximum this graph will ever get in the vertical direction. So your absolute max happens to be at the x value of 8, which was a height of 6. So your absolute max is 6 at x equaling 8. So one of my local maxes is also my absolute max. Now, do I have an absolute min? No, because you're going to negative infinity. It's dropping continuously, so we don't have an absolute min, we only have a local min. So that just kind of very quickly gives you an understanding of what's going on. Your local maxes and your local mins, these are called your extrema of your function. Maybe I'll just put extreme values. The plural of extreme is extrema. Okay? So these are your extreme values. Your maxes and your mins are your extreme values. Okay, and I'm going to pull the definition out of the textbook, which is on page 184. So if you look at it electronically, search around for page 184. These make sense, okay, they're well written. And here it is in a lovely little blue box. It says, let f be a function with domain D, then let f have an absolute maximum value at an x value of c if f of x is less than or equal to f of c for all x. That means at c, the height of the function is greater than at any other x value. So in other words, your horizontal value C is producing the highest point on the graph in comparison to any other x values considered. Okay, so your x value C is given the highest point on the graph in comparison to any other x values that you choose. The minimum says that it has an absolute minimum at an x value of C if it is the smallest value for any x value you choose. So here is where everything is bigger than f of C, meaning that f of C is the absolute min. Now remember, not every graph is going to have both an absolute max or an absolute min, and it won't have either one if your end behavior is up and down, you know, opposite ends. So this doesn't always happen, but when it does happen, it's going to happen at one of your local maxes or one of your local mins. So it's very well written. It's really not that difficult to follow that definition. Remember, maxes and mins are vertical values. They're all considered extreme values, but then there's one special absolute, if it exists, okay, if one actually exists. So your extreme values are your local maxes and mins. And then a local max or min might become an absolute. No, you can only have one absolute. Only one absolute, if an absolute even exists. So you can put in here, it might or might not be the absolute. Okay, it might turn out that one of your locals is an absolute also, and it might not. It just depends on the graph. Okay, now here's what I gave you a copy of as an example which we're getting ready to discuss. So this is example 1 on page 185, and you have a copy of this. And it looks like this. It shows you these graphs. You kind of really have to play with these 4 graphs here to get all this to make sense. It says the absolute extrema of the following functions and their domains can be seen. Notice the function might not have a max or min if the domain is unbounded or fails to contain an endpoint. Okay, so looking at part A, all of these graphs are y equaling x squared, but they may be limiting the domain. So the table above is limiting your domain. If you look at the graph closely, you can see that they lighten up the graph when they eliminate it as part of the domain. So you can see they've eliminated this part of the graph on part B of this figure and this part of part C and also this part on part D. I wish they could have just made it a dashed line or something because it's not quite as well emphasized as would be better. But if you look at the first one, you have the full graph. And it says it's y equaling x squared. And it's saying, does it have an absolute max or an absolute min? It says no absolute max. Well, your end behavior is up. Now, they don't ever put arrows on these graphs in these books, okay? But this is continuing to move in the upward direction. So there is no absolute max. But there is an absolute min of 0. The y value is 0. The minimum is the y value of 0 when x is 0. So this is your absolute min, which is a y value of 0. Okay, then in part B, they're really only letting the graph take on the right half of it because look here, they're limiting the domain here from 0 to 2. So you're including your 0 and you're including your 2, so you're really only looking at that dark blue part of the figure now when you're talking about finding an absolute or local maximum or whatever. Well, here you do have a local min and an absolute min at this point at the origin, and you have a max because they stopped the graph with this endpoint when x was 2. So in this case, you have both absolute and max and min. Your absolute min is a height of 0, and your absolute max is whatever the height of the graph is at this point. So if the x value is 2, you put it into the function, 2 squared is 4, so this is a height of 4. So you have on this one, you have a maximum of 4, which is the y value at this solid point, and you have a minimum of 0, which is the y value at this solid point. Then on the next one, they put an open circle in it. So if you have an open circle on the endpoint of your domain, you don't get to include it as a min. It doesn't get to be a local min or an absolute min if it's an open circle. So on this domain, they went from 0 to 2, but they didn't even let you use the 0. So they open circled it. So this one has no absolute min, but it does have an absolute max at the filled circle at the height of 4. And then the last one, they consider all cases where they put open circles on the domain. They don't include the 0 or the 2 because it's in parentheses in the interval. So there is no absolute min or absolute max in that graph. So they're really trying to emphasize the open circles, emphasize it continuing with the arrows on both of them here and your domain being negative infinity to infinity, just to try to really get that to solid in your mind. So they do a very good job of kind of touching all bases there. Okay, really good job. Now if I turn the page, I'll show you a little bit more here on figure 4.3, and I can write that in the notes if you want to kind of know what we've done. Now I'm going to go to figure 4.3, which is on page 186 of this section of the textbook. Okay, and here it is, all these lovely figures, okay. And it's also talking about maximum and minimums. So in this case, it shows a maximum at x2 and a minimum at x1. This one, it's limiting the graph such that it has an absolute max at the left side here at A and an absolute min at B. So these are local and absolute maxes and mins. This one, they didn't tell us the domain, so we have to assume that this is continuing downward. This one's continuing upward. Well, actually, it didn't, did it? Yeah, it did. They're not talking about absolutes here. They're just talking about locals. So they're talking local here. So that is a local max, a local min, a local max, a local min, and these would be absolute also. Then here you have a local min and a local max at an end point and not at an end point of the graph. And then here you have a local min and a max, one at the end point. So some possibilities of continuous functions, maximum and minimal values on these closed intervals. I think that's just a little more information to kind of, again, get it to stick. Here's an interesting picture. Actually, let's take a look at this definition and this picture. Here, this is where we kind of have to be careful when we're talking about maxes and mins and differentiability. You can see here, this is the function. It doesn't extend in either direction. That's it. It's limited from A to B in its domain. This is considered the local and absolute min because there is no lower point on the graph and it's a filled circle. This is considered an absolute max because it's the highest possible point to the graph. And then you also have this local max here and this it says local min. That's where it gets a little confusing. A local min here, this is your absolute min. Why do you think they call this a local min? That's a hard one for me. I want to call it a local max. Why do you think they call it a local min? There you go. It's like if this is considered concave up, and that's the lowest point in the concavity at that point. So you're looking at these as kind of like U's. If you extended this is like your U shape, and so it's the pit of the U shape. And this is the peak of a U shape, and this is the pit of a U shape. So that's why they consider this like a min, because you're kind of visualizing concavity being concave up and concave down, making it a max and a min. So that is kind of interesting. You got to be really careful with this because I have to think about that also. That if you make it look as if it's a U shape, then it'll help you to define it as whether it's a max or a min when you're looking at it. Okay, so those are just a whole bunch of pictures, visions of everything. Okay, so now let's move on in our notes. Okay, so it's kind of flipping through some graphs in the book. All right, so now let's talk about finding the extrema or extreme values. Using the first derivative. Okay. what do you suppose, and think about this, what does the first derivative have to do with the local max or a local min? It would be 0. Okay, think about this. Just looking at the little graph we made up here, at this local min, your tangent line would be a horizontal tangent line, and the slope of your tangent line would be 0 at the min. Here is a max. Your tangent line would be a horizontal line at this point, so the slope of your tangent line would be 0, and the slope of your tangent line is the first derivative. Here, the slope of your tangent line, which is the first derivative, would be a horizontal line, and that slope would equal 0. So the first derivative, I don't have to have we're thinking, but the first derivative should equal 0 pretty much at your extrema, at your extreme values, at your local maxes and mins, values, or at local maxes and local mins. Okay. Something, or almost, yeah, or slow down, depends on where you are. But you're not going the other way until you go on the south side of the x-axis, right? Okay. Okay. So you can sketch it briefly here also, because your notes need to kind of have this pretty clean and neat. If you just kind of do a part of a graph like this, at this point, and they'll call it C, sometimes they'll call it X, but f prime at C would equal 0, because remember the first derivative is the slope of the tangent line. So if you're at that local min, your first derivative is going to equal 0. Because remember, this is the slope of the tangent line. The slope of the tangent line is the first derivative, and if that tangent line is a horizontal line, then that slope is 0 at that local min. Okay. Now, let's talk a minute about what they call critical points or critical values. Some books talk about them as critical values. I would prefer to refer to them also as critical values. Okay, critical values. And there's a definition, and that definition says something like this. Wonder where maybe I should look at it directly before I write it down as an actual definition. I kind of did it very informally. Okay, here it is formally. An interior point of the domain of a function and we'll let the function be f, where f prime is 0, or where f prime is undefined. Okay, where f prime is 0 or where f prime is undefined is a critical point. So critical points or critical values or critical numbers occur when the first derivative equals 0, which we're looking at local maxes and mins, or where the first derivative is undefined. Where the first derivative is 0 or where the first derivative is undefined. Those are critical points. Now let's kind of think about this a minute. I'm going to do a sketch here. Suppose you have a graph that looks something like this. Okay, something like that. and let this be A, and let this be B, and this be C, and this be D, this be E, and this be F. Actually, one more right here. Let this one be F, and let this be G. So let's think about critical points or critical values. Okay? The critical values occur where the first derivative equals 0 or where the first derivative is undefined. Well, we can kind of have a one-sided first derivative coming in from the right, which is going to give us a horizontal tangent here at this endpoint. So A is a critical value. Where's another one? Where is your first derivative going to equal 0? What's another horizontal value? B. Where's another one? Okay, and another one? E. And another one? D. And G. What about F? You are avoiding F. What's the deal? You are hesitant. Think about it. You're hesitant for a good reason. When you look at D and you look at F, what's our problem here? That's where that first derivative is undefined, right? Because you've got a cusp and you have a vertical tangent line. But remember, critical points occur where the first derivative is 0 and where it's undefined, right? So at D and F, this is where f prime of x is undefined, but that is still considered a critical point. Why are those points still important? Well, f is not really so wonderful, right? That doesn't give me a local max or a local min. But at D, that is a local max, right? So we don't want to lose a local max because we're not setting the first derivative equal to undefined options. Well, I tried to do it so that it had a vertical tangent line. Okay, I tried. I tried to make a vertical tangent line there. I tried hard. Okay. So there's a vertical tangent line, and here's a cusp. So we have to consider not just where the first derivative equals 0 to find our local maxes and mins, but also where it's undefined, because right here at this cusp, I have a local max. So I have to look at where it's undefined. Now, where I have a vertical tangent line, that's not doing anything for my local max or mins, but I still need to take into consideration all places where the first derivative is either 0 or undefined to make certain that I catch all of my local maxes and all of my mins. Okay, so then we talk about a little bit of a conclusion before we jump into some examples. Okay, how do I find my extrema? Or extreme values. Extrema is plural of extreme values. I keep using that word. It's a weird word, isn't it? So what you do now is you say, find all critical points, or really critical values is what I call them. That's from me learning from another book. Okay, critical values, and the way you find these is you set the first derivative equal to 0, and you set the first derivative and find out where it's undefined, where it's 0 or where it is undefined. The second thing you do is you also evaluate the function value at the endpoints. Okay, look at that endpoint in that graph at G. That was not a place, and I can move it back up here. I'll show, hold on. Evaluate f of x at your endpoints. The reason you do that is because over here at this endpoint G, and even at this endpoint A, here your first derivative is not equaling 0, right? But that's the end of the graph. And so you're going to miss this local max if you don't check your endpoints. Okay, so you got to check your endpoints. So compare to G above. Compare to G above. That's kind of what we're talking about there. And then, when you want to come up with your absolute, to get the absolute extrema, or the absolute values, they will be the larger and the smaller locals. They equal the larger and smallest, I guess I should say largest and smallest values. Okay, so you find everything and you kind of consider them all local, and then you nail the biggest one and the smallest one as being the absolutes. Got all that? Okay, so part E, examples. That's a good title for examples, part E. Okay. Given that f of x equals x squared on a limited domain of -2 to +1, we want to find the critical values and then we want to find the absolute max and absolute min if they exist. Find any absolute max or absolute min. And they could say just find the absolutes. This would be very easy to graph, right, and be able to answer this. So if you want to graph it and get a vision and then prove it algebraically, you could. Man, this is just a parabola, right? Let's see, when x is -2, the height is 1, 2, 3, 4. When x is 0, the height is 0. When x is 1, the height is 1. So it's going to look like, it's just looking like this. That's what it looks like. So very obviously, it has an absolute max of 4, and an absolute min of 0, and a local max at 1. Okay. We know all this. Okay, but now let's show it algebraically. Okay, so what are my critical values? In case the graph was not so simple. My critical values occur when f prime of x equals 0, or when f prime of x is undefined. And or. Okay, so f prime of x. F prime of x equals 2x. Where does 2x equal 0? When x equals 0. So there's a critical value. Okay. F prime of x equals 2x. Does 2x ever equal undefined? Can 2x ever be undefined? No. Okay, you're only looking at undefined situations if you're taking the square root of a negative number or you have 0 in the denominator. Okay, that's your undefined situations. You got a fraction and you can get a 0 to happen in the denominator, or you have a radical and it can be, the radicand under the radical can be 0. So there's no problems with this. I'm not going to have anything undefined. So I only have one critical value, right? But that's not going to tell me all my locals, maxes, and mins, right? So right now the answer to this question is a critical value. The only one it is x equaling 0. That's the answer to part A. Part B is asking me for the absolute max or min, the absolutes. Okay, to find the absolutes, I take the function value at the criticals and at the endpoints. Find the function value at the critical numbers or the critical values and the endpoints. Okay, you got to do it at both. The endpoints of the interval. The endpoints of the interval. Okay, so my critical value is x equaling 0, so f at 0 is going to be 0 squared, which is 0. Okay, then my endpoints. One endpoint is x equaling -2. So f at -2 is -2 squared, which is 4. And the other endpoint is x equaling 1. These are the endpoints of the interval from -2 to 1. X at 1, f of 1 is 1 squared, which is 1. So there's your three values. So what is your absolute max and what is your absolute min?
0, 4.
There you go. The absolute min is 0, and 4 is the absolute max. Now, had we not looked at the endpoints, we would have missed the absolute max, right? Had we not considered the endpoints, we would have missed the absolute max. We knew the absolute max was going to be 4 because we graphed it and saw it. But the only way we're going to get it algebraically is to evaluate the function at the endpoints to make certain that the endpoint is not presenting an absolute for us.
So you just write the x value, you don't have to write the
Those are the y values, not the x's. Okay, those are y values. Careful. No. No. The y value is the min, the low. Yeah, and they're going to say absolute value. They're not going to say absolute point. Actually, I've never heard of that. They don't use that word. Okay, they'll always say absolute value, which is the y value at the point, which is normally, okay, a local max or local min. Okay, so let's try another one. Okay, I really was detailed, very specific, because this can get terribly frustrating if you're not catching it. Okay, suppose we're given that g of x is our function, and it's 8x minus x to the 4th, and they're limiting the domain, so we're losing all the end behavior business. So we're giving the interval, or the domain, of -2 to 1. They want to know what are the critical values and what are the absolutes. So part A is what are the critical values, and part B are what are the absolutes, if there are any. There might not be, but because this is limiting the domain, there probably is, okay? Okay, so critical values occur in two places. They occur where f of x equals 0, where f prime of x equals 0, and where f prime of x is undefined, or g prime of x in this case. Okay, so g prime of x equals 8 minus 4x cubed. Now, remember, I'm going to set g prime of x equal to 0, and I'm going to set g prime of x to find out where it's possibly undefined. So it's kind of like the undefined business is catching the cusp, the height or the low at a cusp. Okay, so if I'm setting this equal to 0, this becomes a negative 4x cubed equaling a negative 8, or an x cubed equaling 2, or x equaling the cube root of 2. So one of my critical values is at the cube root of 2. I have no clue if it's a high or a low or an absolute, but I'm thinking you got a little, hump or a dip here, which is occurring at an x value of the cube root of 2. Okay, is it ever undefined? G prime of x equals 8 minus 4x cubed. Can I ever make that undefined? No. You're only going to get undefined stuff with radicals or rationals, and rationals are where you have fractions. Okay, so I don't have a fraction, I don't have a rational, so this isn't happening, not going to happen. Okay, so here's my critical value. That's my answer to part A. Now part B is, do I have any absolutes? Okay, my absolutes are to take my function value at my critical value and to take my function value at my endpoints of -2 and 1 and compare the heights at all those points, the heights at the endpoints and the height where my first derivative is 0, which should either be a max or a min, a local max or min. Okay, so cube root of 2. Now you're going back to your, this should be g. I'm sorry, y'all should have hollered. These are all g's. This is a g of x function. So g of x, our original function, is 8x minus x to the 4th. So this is going to be 8 times the cube root of 2 minus the cube root of 2 to the 4th power. So this is 8 cube root of 2 minus the cube root of 2 to the 4th. The cube root of 2 cubed is 2, right? Times 1 more 2 is a 4. So this is 8 cube root of 2 minus 4, which I think, well, I didn't figure it. Okay. What is the cube root of 2? Somebody tell me. What's the decimal? Yeah, what is the decimal value of the cube root of 2? So guess what? I'm going to take this out of the whole picture here. Why? No. No. Look at the domain on this thing. It's outside the domain, isn't it? If I didn't limit the domain and the function kept going, I'd probably have a local max or a local min there. But it limited my piece of the graph, so I don't even get to use that critical value. Okay? So honestly, there are no critical values because this one came out outside the domain. So that's going to drive you crazy. That one's going to drive you crazy. Okay, g of negative 2 then is 8 times negative 2 minus a negative 2 to the 4th power, which is a negative 16 minus 2 times 2 is 4 times 2 is 8 times 2 is 16 to the negative 32. And then g of 1 is 8 times 1 minus 1 to the 4th power, which is 8 minus 1, which is 7. So evidently, I have my endpoints are doing it all today. So here's my absolute min, and here's my absolute max, which is a vertical value. It is the ordered pair negative 2, negative 32, but to get your min and max, they just want the y value. They want the height of the function. So the negative 32 is occurring at an x value of negative 2, and the 7 is occurring at an x value of 1, but you only want the vertical values. And this graph, just to let you know, this graph looks like this. This graph looks something like, come on. Blue screen, go away. Wake up, computer. Okay. So it looks something like this. And then it goes and it dips down. But right here is our limited domain of 1. Okay. So this would have been that x value of the cube root of 2, but we don't get to have it because it limits. We don't get to have any of this because it's limiting our domain to 1. So you get your absolute min over here at this endpoint and your absolute max over at that endpoint, and you don't even get to have a critical value in that domain. Sneaky, sneaky. Believe me, they will do that. Okay. Okay, so suppose we go back to another function, let it be f of x instead of gx this time, and suppose it's x to the 2/3. And they limit this domain so that it is on the domain or within the interval of negative 2 to 3. Again, they're asking me for critical values, and they're asking me for if an absolute exists, what is it? Okay, so part A, let's find the critical values. And I usually write that CV, critical values. And then we'll find if there's any absolutes. Okay, so the critical values occur when the first derivative equals 0 or when the first derivative is undefined? Okay, oh wow, the first derivative of this thing. Okay, the first derivative of this function is 2/3 x to the 2/3 minus 1, which is a negative 1/3. Or in other words, the first derivative is what? 2/3 cube root of x. Does this, and now I'm supposed to set this equal to 0 to find the critical value, right? This is my first derivative. This is the slope of the tangent line, instantaneous slope of the tangent line at any point along the graph. My goal is to set this equal to 0 to get an x value that will give me a critical value. Will that ever equal 0? No, it never will. So I'm not getting any critical values off of having a horizontal tangent line for this graph. Okay, is there any place where the first derivative is undefined? Again, we just figured that the first derivative was 2/3 cube root of x. Is this ever undefined?
Yeah, 0.
There you go, when x equals 0. Now, there might be a cusp there, or there might be a vertical asymptote there. Okay, we're hoping a cusp because it will give me maybe an absolute or a local max or min or something. Okay, so this is my only critical value for this function. And that's occurring when my first derivative is undefined, so I'm not visualizing any of these, peaks and dips and this little U-shaped stuff going on in any concavity. I'm just seeing, oh dear, there's either a vertical tangent line there or there's a cusp there in order for that to be 0. Okay, so now let's talk about absolutes. Well, to go through the order of how in the world to do this, we're supposed to be evaluating the function values at the criticals and at the endpoints. So we're going to be looking for f at 0, because this is coming from your critical value, and then your endpoints are going to give me f of negative 2 and f at 3. Okay, so you're looking at your critical value place to look for a local max or min, which we're going to hope maybe will be an absolute, and then at the endpoints to see if they're local maxes or mins and maybe absolutes. So going back to my f of x, being x to the 2/3, my original function, not my slope of my original function, f of 0 would be 0 to the 2/3, which is 0. That's not very high or very low, but I don't know, it might be good. F at negative 2 is negative 2 to the 2/3 power, which is the cube root, right? Remember your rational exponents. This is the cube root of negative 2 squared, which is the cube root of 4, which I don't know what that equals. Oh, I did bring one of my little TIs. Math teacher should never leave home without a TI, right? I have had one in my purse before, and I thought, oh my goodness, I can't believe I'm carrying this around in my purse. How stupid. When I'm just like out shopping or something, or you've gone to the zoo and there's a TI in your in your purse. People look at you kind of weird. You're digging for your wallet and you pull out a calculator. Okay, so 3 to the 2/3 is the cube root of 3 squared, which is the cube root of 9, which is going to be bigger than the cube root of 4, but still. Well, that's a 2.08. Okay, so do you see an absolute? Yeah. Are we within our interval? We got to be really careful. Negative 2 to 3, yeah, all these values are in our interval because we're including the endpoints. Boy, if they had thrown a parentheses on this thing, we'd be in trouble, right? If the interval had been a parentheses and square bracket instead of a square bracket, we'd be in trouble. Okay, so it looks to me like this is my absolute max, and this is my absolute min. And I wonder what was going on at the x value of 0. That's not right. That's, duh. This is my absolute min right here. I'm still thinking about the zoo. I did go last weekend, okay? I did not take my calculator, though I have made that mistake before. So I wonder what in the world this graph looks like. We have some lovely information here, but I have no vision of this thing. Here's what it looks like. It has a cusp. Okay, so over here at -2 and over here at 3. It's doing something like this, just above the 2. And then at the 3, it's got to be, how did it do that? I don't remember. No, at the +3, it's here. So here it must have been a little bit lower or something. Q, yeah, right in here. X that one. It did this. It's a cusp. Looks like that. Okay, so you have two local maxes, which really are, two local maxes occurring at -2 and 3, and a local min, which is absolute on this interval, at 0. But remember, the first derivative was undefined at this cusp, which gave me my absolute min. Okay? So when you're looking for the absolutes, it's going to be really hard to remember to check the endpoints, but it is hard to check the endpoints. I don't know why that's such a difficult thing to remember, but it's hard to remember to check the endpoints because you're so geared on that first derivative. Okay, you're so stuck with taking that first derivative and getting it set equal to 0. Okay, so now we're going to do some additional examples, a little bit different. I mean, all those are exactly the same. Find the critical values and find the absolutes. Okay, so now we're going to do some additional examples, getting away from that standard question. Okay, and I'm actually pulling this straight from the textbook. This is number 43 on page 191 if you want to look at it in the book. But the question says, well, I can pull it up. What does the question say? It says, determine all critical points. That's all they're asking me. Find critical points. Find critical, and they did say point. They didn't say critical value. They said critical point. Your critical value would be your x value. Your critical point would be the x and y to match it. Okay, so pay attention to what they're asking. And here is the function they've given. F of x equals x times 4 minus x cubed. So now they're going to start playing with you a little bit algebraically and making certain you're good at using all your rules of differentiation. Okay, so to find the critical points, well, there's two things. We're going to set the first derivative equal to 0 to find those x values where there's going to be local max and min with a horizontal tangent line. And we're going to take the first derivative and see if there's any place where it's undefined. Two things. Okay, so what in the world is the first derivative? It's going to take me a minute to make this happen. Okay, the first derivative is the product rule. The first, which is x times the derivative of the second. The derivative of the second is going to be the chain rule. So the derivative of the second is the 3 times the 4 minus x to the 3 minus 1 times the derivative of that binomial, which is -1. That's the first times the derivative of the second. Plus the second, which is 4 minus x cubed, times the derivative of the first, which is just the derivative of x, which is 1. Okay, so this is a -1 times x times 3, which is a -3x times 4 minus x squared plus 4 minus x cubed. Now think about what you're getting ready to have to do with this. You're going to have to set this equal to 0, right? And you usually like stuff in factored form before you set it equal to 0, right? And then you take each factor and set it equal to 0, the 0 product rule, I love it. Okay, so we're going to factor. Okay, so we're going to take the 4 minus x squared. Here's the first and here's the second. So you're going to take the 4 minus x squared out, and it's going to leave behind a -3x plus what? Plus 4 minus x. There you go. So this is 4 minus x squared times a negative 4x plus 4. Now you can factor 4 out if you want to. I don't care. But you're going to have to set this thing equal to 0 up here to find your critical values. So here comes the process. Setting this thing equal to 0 to see what critical values we come up with is to set this 4 minus x squared times this negative 4x plus 4 all equal to 0. This is called the zero product rule, which means you set the 4 minus x equal to 0 and you set the negative 4x plus 4 equal to 0, right? You set the two factors equal to 0. So you're going to get what? X equaling 4 is one critical value and x equaling 1. It is, which you take 4 minus x times 4 minus x, right? Which is going to give the same outcome. It's called the double root kind of thing, remember? So there's two critical values. And then the other part was, is this first derivative ever going to be undefined? Can this product ever be undefined? No, it's not a radical and it's not a rational, it's not a fraction, and there's no issues here. So this isn't happening. So we get two critical values, here they are. We're visualizing a local max, a local min, possibly. Maybe they'll turn into absolutes. But that's all they asked. That is your answer. So you're going to do all this algebra and you're done, you got the right answer. But in the back of your mind, you should be thinking, those are probably local maxes and mins to whatever this function up here looks like. Okay? This is a fourth degree function. Its end behavior is going to be what? I think it's going to be opposite because it's going to be a negative fourth degree function, right? It's going to be a negative fourth degree function, so it's going to be down in behavior, so you should have an absolute max out of one of those.
So that's just half the answer, right?
That is the answer. All they asked, oh, they said points. I don't like that part. That's extra work. Okay, if I put a 4 in here, I get 0. That's a good one. Do that one. If I put 1 in here, I get 1 times 3 cubed.
Yeah, it's x equals negative 4. No, minus 4.
Negative x equals negative 4, so x equals 4. 4 minus what equals 0? Okay. The moment of humility, right? Y'all do it to me all the time. Okay. Okay. All right. When x is 1, it's going to be 1 times 3 cubed, and 3 cubed is 27. So it looks like there might be a lovely absolute max right there. Right there, right there. No, not absolute, local. Well, yeah, it would be absolute if this thing has end behavior of down. Ooh, look at this one. This is fun. Again, I'm going to change it. Critical values. I don't like having to plug it back in. That just takes time. And suppose y equals x squared plus 2 over x. Okay, remember critical values occur when the first derivative equals 0 and when the first derivative is undefined, which means we're trying to hit all those local maxes and mins and not miss any of them. Okay, so let's take the first derivative of this thing. The first derivative is what? 2x plus, oh dear, I got to rewrite this. This is x squared plus 2x to the negative 1, right? That's a lot easier to differentiate that. So the derivative is 2x plus a negative 2x to the negative 2, which will be rewritten as 2x minus 2 over x squared. Now, to get the critical values, I'm going to set this y prime equal to 0, which means I'm setting this 2x minus 2 over x squared equal to 0. Well, that's not fun to do unless the denominator is the same. So I'm going to get an x squared denominator, which will make this numerator 2x cubed minus 2, right? I said cubed, and I wrote a 2. 2x cubed minus 2. Now, what makes that equal 0? Only when the numerator is 0 does the fraction equal 0, right? Only when the numerator is 0 is the whole fraction equal to 0. So when is 2x cubed minus 2 equal to 0? When x cubed is equal to 1, or x is equal to 1, right? There's one of my critical values. The other option is to set your first derivative so that it's undefined. Okay, when is 2x minus 2 over x squared undefined? When x equals 0. When this guy right here, this denominator is 0, I guess I should put when x squared equals 0 or when x is 0, that causes the first derivative or the slope of the tangent line to be undefined, which is either happening at like at a cusp or at a vertical asymptote. So here are the critical values to this function here. And that's all they ask. They're just really playing with you algebraically here. They're not having you graph. They're not having you determine if they're maxes or mins or absolutes or what. They're just having you algebraically come up with the critical values. That's not a big deal. Okay, I'm going to take this one from the book, number 51 on page 191. And the question says, okay, number 51 says, right here, find the extreme values, absolute and local, of the function and where they occur. Where they occur, what does that mean? Where they occur? Find the extreme values. They occur in the real number system. Okay. Okay, let's play with this. Okay, so find the extreme values find the extreme values, absolute and local. That means find the local maxes and mins, and if any of them are absolute, let's define them as absolute. Okay, so now then, here is our equation. Y equals x cubed plus x squared minus 8x plus 5. This is a cubic, it's a third degree equation. It's going to have an in behavior of down on the left and up on the right. So it doesn't look like anybody's going to be absolute on this one, right? Unless they give me, did they give me on this one a, they didn't limit my domain. Okay. Here we go. Find the first derivative. First derivative is 3x squared plus 2x minus 8. My critical values are going to come up where this first derivative is either equal to 0 or this first derivative is undefined. Well, the first derivative is equal to 0 when 3x squared plus 2x minus 8 equals 0. We just hope this thing factors, and boy, if it doesn't, you got to go to the quadratic formula. Two and 4, 4 and 2, positive 6 and a subtraction of 4. There it is. Okay, so then you get, this is called the zero product rule, where you take each factor of the product and set them equal to 0. So one of them is an x value of 4/3 and the other is an x value of -2. And this cubic function has in behavior down on the left and up on the right, so neither of these guys could dare to be absolute. but they probably are local. Now those are the x values. So if we want to know the local max or mins or extrema, wait, is there any place where this is undefined? I've become distracted. Forgot this half of the question. No, this isn't happening. Okay, so the extrema, we don't have any endpoints, so we're going to find the function values at these criticals. And I think I cheated and looked this up in the back of the book, so I didn't feel like putting it in. Negative 41 over 27, oh fun, and 17. Now, if you don't trust yourself here, that these are locals and not absolutes, then just pick up your calculator and graph this thing to confirm. And I don't know if I opened up my Smart View or not. Did I? Get off of there. Here we go. How would I know that? I just know it because I know the end behavior is down on the left and up on the right. I think you just have to know the graph on this one because there is no limitation on that domain. It's not an oscillating function like a trig function. There's no endpoints involved. I think I would just have to graph it. I just happen to know that. I think y'all know that too, what that graph sort of looks like. That end behavior on a cubic. Smart View takes so long to open. I guess I should have done this before I started the recording, right? Hurry up. There it is. Okay. All right, so the function was, let's get rid of all this stuff. I think Miss Coleman has been in here messing all this mess up. Okay, so this is x cubed plus x squared minus 8x plus 5. And we don't need too big of a window, but it probably needs to be at least be a zoom integer. Now what's it doing? That wasn't quite big enough. It almost was. I need to be a little bit higher. That's not a zoom integer window. Yeah, look at that pretty graph. Didn't I capture it well? Okay, so you can see from this graph, which I can't touch this with my pen. I can't point at it even. Wait, where's my cursor? Okay. Here is a local max, which we came out to be at -2. Here's an x value of -2. We nailed it. Okay, my x value is -2, and that's my local max. Here is my local min at an x value of 4/3. And boy, this is continuing downward and upward, so there's definitely no absolutes in this picture. So we did just fine. So this is a local min and a local max. Okay, those are strictly locals. So it went like something like this, right? Look like that. It was better than that, but that's kind of what it looked like. Okay, it was a lot better than that. That was a terrible sketch of it. Hurry up and get that away so we don't have to look at it anymore. Okay, so here's another one. Let's take a look at number 53 in the textbook. And it was y equaling the square root of x squared minus 1. And again, this is in the same category of questions, so it's asking to find the extreme values, which are local maxes and local mins, and if there's any absolute. Okay, I guess I can maximize the screen. Okay, so we know what we got to do. We're going to take the first derivative and set it equal to 0 and take the first derivative and see where it's undefined, so we capture all options. So we've got to figure out what the first derivative is. I'm going to make this a 1/2 exponent. So when you do the first derivative, you're going to have to use the chain rule here. So it turns out to be what? X over, there you go, the square root of x squared minus 1. Okay, so we're going to take the first derivative and we want to set it equal to 0. And we want to figure out where it's undefined. Okay, so if I set this x over this square root of x minus 1 equal to 0, then only the numerator, when the numerator equals 0, the fraction equals 0. So there's one critical value. And then if I want to see where this is undefined, wow, where is it undefined? Okay, it's undefined when x squared minus 1 equals 0. So this would be x squared equaling 1, or x equaling the square root plus minus 1. We have no endpoints given to us on this domain. But let's stop for a minute and think about this. What is the domain of this function? Y'all know? What is the domain of this thing? Domain is everywhere so long as x squared minus 1 is greater than or equal to 0, right? How did we do these? Y'all remember this? Remember all that? Oh, yuck. And then you had to do a sign graph? Y'all remember? Okay, where you put what? A -1 and a 1? Then you picked a value like -10, which would be positive. You pick 0, would be negative, and you pick like +10, which is positive. So your domain is from -infinity to -1 and 1 to infinity. So your domain is -infinity to -1, including -1 and 1 to infinity. So this must be a pretty weird looking graph, right? Actually, it looks like this. It goes like that. The graph is kind of weird looking. It looks like that. That's your sign graph. Your x squared minus 1 is positive to the left of -1 and positive to the right of +1 and negative in the middle. That's called your sign graph from long, long, long time ago. Okay. So if we're looking for the extreme values, this is pretty weird. Okay, you're looking where x is 0, where x is 1, and where x is -1. How did we get an x value of 0? Okay, what about this x value of 0? Let's discuss this. You can't count that. Why? It's not in the domain. If you put 0 squared minus 1, that's the square root of -1, which is not a real number. This is not in the domain. We just discovered over here it wasn't in the domain, because the domain is going to be from -infinity to -1 and 1 to infinity, so that's not even in the domain. Okay, when x is 1, f of 1 equals the square root of 1 squared minus 1, which is 0. And when it's negative 1, it's negative 1 squared minus 1, which again is 0. So those are my extrema. They're either local maxes or local mins, or what in the world are they? Well, if you look at the graph, they're both absolute and local min. They didn't ask for the points, but this would be if they asked, well, they're not going to ask that. So this is a local min and absolute. Because this is what the graph looks like up there. So it doesn't hurt to have the graph available to you and paying close attention to the domain. When you get into these radicals, you're going to have limited domains. So be really careful. We're not done. We just have a couple more examples to go, but they're kind of interesting, so we don't want to forget about them. But I'm going to pause the recording. Let's take a break. Okay, so let's finish this recording. So we're going to look at a couple more examples. You are going to be good at this section when we're finally done. Okay, so now we're going to look at example number 61 on page 190. And this is a most interesting question. So we got to really read this question here. Okay, here it is. Here's all these lovely questions underneath. It says, find the critical points, and they're points, not values, critical points, domain endpoints. What in the world are they talking about? The domain endpoints and extreme values, absolute and local, for each function. Okay, so that's a very interesting question. And which one did I pick to do? Number 61, this one right here. Okay, so here's what the question says. The question says, find the critical points then it says to find the domain endpoints. I've got to figure out what they're asking there. That's an interesting question. The domain endpoints. And then to find the extreme values and then in parentheses they put absolute and local for the function. That's the question. And here on number 61, the equation is y equaling x times the square root of 4 minus x squared, and close it off. All right, so critical points are going to come in here whenever we do y prime equaling 0 or when y prime is undefined. But I also want to talk what this domain endpoint business is all about. Let's think up front. I'm going to play with this information. What is the domain of this function? Well, if you have a radical, this information on the radical better be positive or 0, right? So in other words, the domain is occurring when 4 minus x squared is greater than or equal to 0. Positive or 0. So what does this mean? Well, this is what? Negative x squared plus 4 greater than or equal to 0? Which is a negative 1 times x, negative 1 times x squared minus 4, which is a negative 1 times x plus 2x minus 2. So we're playing with what? A negative 2 and a positive 2. So the domain on this function, without having to go through an entire sign graph for you, the domain is running from negative 2 to positive 2. And so when they talk about the domain endpoints, that means this original function, though they didn't limit the domain by giving you an interval, the domain is limited by the radical. And so when you look for your extreme values, when you're looking for your local maxes and your local mins, you need to look at it at these two endpoints, though they didn't give that to you to begin with. So you're having to find your own domain to come up with your own endpoints for this function. So that's going to kind of help us out when we come to trying to find local maxes, local mins, and absolutes. Okay, so let's do the first derivative. Well, to make the first derivative happen, I'm going to rewrite this as 4 minus x squared to the 1/2. So when I come in here to try to calculate the first derivative and set it equal to 0 in the first derivative and set it to undefined situations, this is going to be the product rule with the chain rule nested into the process. So the first is x times the derivative of the second, which is 1/2, times 4 minus x squared to the negative 1/2, times a negative 2x. That's the first times the derivative of the second, plus the second, which is 4 minus x squared to the 1/2 times the derivative of the first, which is 1. This is just finding the first derivative of the function, people. So this is a negative x squared times 4 minus x to the negative 1/2 plus 4 minus x squared to the 1/2. Now if I factor out a 4 minus x to the negative 1/2, it's going to leave behind a negative x squared plus what? It's just the first power.
If you 4 minus x squared.
Oh, are those? Oh, okay, sorry. Yeah. Little twos on here. Ah. Here we go. So this becomes 4 minus x squared to the negative 1/2 times, this is a negative x squared minus x squared, so this is a negative 2x squared plus 4. So this is, are we ever going to get to the end? Negative 2x squared plus 4 over the square root of 4 minus x squared. This is your first derivative. Now to find your critical values, you're going to figure out where this first derivative equals 0 or where this first derivative is undefined. So it equals 0 when a negative 2x squared plus 4 over the square root of 4 minus x squared equals 0. And for a fraction to equal 0, the numerator would equal 0. So this becomes a negative 2x squared plus 4 equaling 0. Negative 2x squared equaling a negative 4. X squared equaling a 2. Or x equaling plus minus the square root of 2. Now where the first derivative is undefined is where a negative 2x squared plus 4 over the square root of 4 minus x squared is undefined, is when the denominator is 0. For the denominator to be 0, 4 minus x squared would have to equal 0. Negative x squared would equal negative 4, or x squared would equal 4, or x would equal a plus minus 2. So we have 4 critical values here. Now this can get pretty, you got to get this kind of organized. And this is the way they do it in the book, which is pretty nice. And in the book they make a table and they say, let's list the critical values. Then let's list the first derivative of the critical value. Then let's list the function value at the critical value. And then we'll determine the extrema, meaning if it's a local max or a local min. Well, our critical values in order are negative 2, negative square root of 2, positive square root of 2, and positive 2. There's the 4 critical values we came up with. The first derivative at negative 2 was where it was undefined. At the square root of 2, it was where it was 0. And at the positive 2, it was undefined. So that kind of tells me if I'm looking, at where there was a horizontal asymptote or where there was possibly a cusp or a possible vertical asymptote. That covers all those grounds. Yes. Move some stuff out of the way. Y'all gotta tell me when I do that, because I'm so busy looking at my own piece of paper that I'm not catching. And there's a mess in this corner beside me. It's crowding me. Miss Coleman brought that in here. That looks just like her. I love Miss Coleman, so I'll have to talk to her about that. Okay. Now, f of x in this case is what is the function value at -2. So I'm going to put up here this part, f of x equals x times the square root of 4 minus x squared. So if x is -2, this is -2 times the square root of 4 minus 4, so it's -2 times 0, so this is 0. Okay, so this just, these could be ugly numbers, but in this case, they're working out nicely, okay? If it's a negative square root of 2, this is a negative square root of 2 times the square root of 4 minus square root of 2 squared, which is 2. So 4 minus 2 is 2. Oh dear, I don't know if I can do that in my head. F of a negative square root of 2 would be a negative square root of 2 times the square root of 4 minus the square root of 2 squared. Oh, good grief. Which is a negative square root of 2 times the square root of 4 minus 4, which is 0. So it's just a negative square root of 2. Is that right? A negative square root of 2. I got here it's supposed to be -2, not negative square root of 2.
Yeah, it'd be square root of 2 times the square root of 2, which is 2, which is 2.
Oh, because that's 4 minus 2, which is 2. There we go. So the negative square root of 2 times the square root of 2 is -2. Get that on there in that pen. And then this one's going to be 2, and this one's going to be 0. Okay, so these are the heights of your functions. This is like an ordered pair, -2, 0, negative square root of 2, -2, square root of 2, 2, and 2, 0. These are like your ordered pairs on your original function. So if your height is 0, your height is -2, your height is 2, and your height is 0, then it appears to me that this is a local max, and this is your absolute max, and this is a local min, and this is an absolute min, which is what they were wanting. But you know, I would never really trust myself when you have a nice fancy little $120 Ti that I end up carrying in my purse too much of the time to the zoo. I would want to confirm this, and I really would. I would come in here and I would just pull my calculator to see, am I on track or not? So if you were to graph this thing on your calculator, and notice that we did get lucky. If you go back up here, remember, I'm going to slide the page, it's going to make you a little bit dizzy. Remember, your domain was from -2 to 2. So we really got lucky that we hit the -2 and 2 values whenever we were doing these criticals. So the criticals were actually on our endpoints of our domain. But if you graph this, it looks like this. To confirm if I'm on track or not, let this be -2, let this be 2. So negative square root of 2 somewhere over here, and positive square root of 2 somewhere over here. And it starts here, it drops, swings back up, kind of has a peak, and drops. And so it does work that you're seeing like a min, a max, absolute max, and absolute min, and local max and local min. So it does work. Okay, we were on track. We are exact in that regard. So this little table right here is kind of nice. And you want to think about doing this table when you have several of these critical values to kind of keep you on track. And then I really would always confirm with a graph. I really would. Okay, we have finished this section. We only covered one section, and that is okay. We will be all right because I've looked ahead. We're on track. Y'all have a good weekend. Be certain you're in there playing with that homework.